Hello, I'm Anant Agarwal. I'm a professor in the Department of Electrical and Computer Engineering at the Ohio State University. This is the first lecture in the video course series on silicon and wide bandgap power devices. I would like to acknowledge the support from Office of Naval Research for this video course on wide bandgap power devices, and I would also like to acknowledge the support of my colleague Dr. Arash Salami, who has worked very hard in preparing this course with me, and he deserves as much credit as possible along with my other team players in the research group here at Ohio State. So with that, let's start with this first lecture. There are 4 textbooks that we would like to provide references for as we move in this course. The first one is on power electronics by Professor Ned Mohan and his colleagues, and that describes the power electronics elements such as buck converter, boost converter, power converters of various types. The second book is a device book, specializes in silicon carbide technology by Kimoto and Cooper. The third book also provides a very comprehensive review of silicon and silicon carbide power devices. And finally, the book by Professor J. Baliga on gallium nitride and silicon carbide power devices. So all these 4 references are excellent references, and we'll draw from them at various times as we move into this course. Here's a brief outline of this course. We will start with a very fundamental introduction to power devices, which is basically the purpose of this first lecture, and then we will provide you basic background on fundamentals of semiconductor, talk about material properties, and then we will talk about Schottky diodes and pin diodes and edge terminations, key advantages of silicon carbide power devices, and then we will get into power MOSFETs and gallium nitride edge FETs or HEMTs, which are high electron mobility transistors, finally silicon IGBTs, and also talk about key advantages of silicon carbide power devices again to remind you about what the key advantages are with respect to efficiency and power losses, and then we'll give you an introduction of design and processing of wide bandgap power devices and some packaging considerations for packaging these devices. So first lecture, introduction to basic power devices. Here we show a big picture. On the left hand side here we have a cartoon of a power MOSFET. This is a chip we fabricate, and then it can be packaged into a discrete package such as the one shown in the middle, or power module here where we put multiple devices in parallel to increase the current rating. Then once we have packaged the devices, we can build power electronic systems such as an inverter, and here we show a silicon inverter along with silicon carbide inverter, and you can see the size reduction that is possible by using silicon carbide. All right, so now looking at the spectrum of applications for power devices. They range from 5 watt to 100 megawatt in systems such as phone chargers, laptop chargers, home appliances, PV converters, hybrid electric vehicles, charging stations, and so on, all the way up to the grid based applications. So, as we use power devices in these various applications, the voltage and current ratings of these power devices will depend upon the power rating of the application, and also the type of device we use will also depend on the power applications, as we will see. So, basically the power electronic circuits can be divided up into these 4 categories: DC to DC, DC to AC, AC to DC, and AC to AC converters. The last one, AC to AC converters, also called cycloconverters, are not very common, but nevertheless they can be built and developed and manufactured. They offer certain advantages in terms of higher efficiency as we go directly from AC to AC. But generally DC to DC are very common, DC to AC inverters are very common, and of course AC to DC rectifiers we see in industrial heaters and also the first stage of phone and laptop chargers. So, we will look at some of these examples where these devices are used. So, here is a typical phone or laptop charger configuration. Input is anywhere between 100 to 240 volt AC coming in, and output is a regulated 5 volt DC for phones and 14.5 volts, for example, for Mac, could be 20 volts for other types of laptops. So, the first stage converts the incoming AC signal into an unregulated DC signal. So, this is an example of a rectifier stage. And then we have a DC to DC bus, which then converts DC to DC and creates a regulated output for the phone or the laptop. So, this is one example where we can go from AC to DC using 2 stages. Here is a typical example of DC to AC application such as PV converter. Input is a 100 to 300 volt DC coming from a PV panel, and output is a AC line voltage, say 220 to 240 volt AC, or it could be any other value. If it's a single phase, it could be 110 volt AC. So, the first stage is converting the incoming DC into a higher voltage DC, so say roughly 700 volt. And then the purpose of second stage is to take the 700 volt DC and convert it to a regulated AC with a RMS value of 220 to 240 volt AC. So, again, this is very widely used in PV converters, this kind of configuration. The details may change depending upon the input and the output needed, but the principles are the same. Here is an example of hybrid electric vehicle and electric vehicle application. So, the first one is pure internal combustion engine or IC engine, where we have an internal combustion engine driving the transmission, which then drives the wheels. Then the very simple uh, diagram for a pure electric drive is shown on the top right. You can see that the power is stored in the battery, which is then processed by a converter, which converts the incoming DC voltage into a three-phase AC voltage that basically is used to turn the motor, and the motor then turns the wheel. So, this is an example of pure electric drive. Bottom left is a hybrid drive, and it's also a parallel hybrid drive. So, here what is happening is that we have energy storage in the form of battery, which gets converted by a power electronics converter into three-phase AC to supply power to the motor, but at the same time we have in parallel an internal combustion engine which is driving the transmission and the motor. So, motor has two power sources, one from the IC engine and one from the battery, and this is called parallel hybrid drive. Depending upon the load requirements, the engine can be shut off, or the power from the battery can be shut off, or sometimes during braking the power can go back into the battery. So, this is a highly complex system, but works very efficiently in automotive today. The last one is a series hybrid drive, also used in certain kind of applications, where the IC engine essentially turns a generator, which creates a three-phase AC output, which is then processed by the power electronics converter and can charge the battery as well as provide power through another converter to the motor, which then drives the wheel. So, you can see that the power electronics can be used very effectively in pure electric drive and hybrid drives for automotive. Here is an example of a DC to DC converter. This one is a buck converter. So, essentially in this converter we have a DC coming in, which is source voltage V1, and we have a switch, and we have a diode. The diode only allows current to flow in one direction, in this case from bottom to the top. So, let us say that the switch is on, then the power flows through the inductor L, builds up the current, which flows through the output resistor R. Then when the switch is off, this power continues to flow through the diode and the current reduces slowly. And the idea of this DC to DC converter is to convert incoming voltage V1 into V2, where V2 is less than V1. And we can simply accomplish it with one inductor, one transistor, and one diode. So, here are the detailed waveforms. So, here the switch is on and then the switch is off, and that duty cycle is D, which is T on divided by the total time period, and you can see that D is going to be less than 1. So, the inductor current obviously is the current that flows through the inductor, and you can see that the current builds up when the switch is on, and then the current reduces linearly when the switch is off. And when the switch is off, that inductor current is the same as diode current, and when the switch is on, that inductor current is the same as the input current through the switch. So, one can show that in this situation the output voltage is capital D times V in, and since D is less than 1, this is a buck converter which reduces the output voltage. So, this is a classical DC to DC converter where we are using one switch and a diode and an inductor. If we reconfigure those switches and diodes and inductors in this way, then this becomes a boost converter where the output voltage V2 would be greater than V1. So, in this case, when the switch is on, the current builds up through the inductor, and then when the switch is off, the current continues to flow through the diode and through the load, and one can show that V2 is V1 divided by 1 minus D, and since D is less than 1, V2 would be greater than V1. So, again DC to DC conversion can happen with a diode, a switch, and an inductor. An example of an inverter where we are converting DC into AC. A good application is motor drive. So, here we have a source of DC voltage V1, which is divided up to two sources V1 over 2 across these two capacitors in series, and then we have two switches and two diodes across these switches, and these diodes are called the freewheeling diodes or anti-parallel diodes, and they are labeled as TA plus and TA minus switches, and then the load is connected between the switch and the center of the capacitor bank. Now, on the right hand side, we show the waveforms for the output voltage V2 across the load. So, when TA plus switch, when the top switch is on and the bottom switch is off, you can see the voltage across the load V2 would be V1 over 2. And when we reverse the conduction of the switches such that top switch is off and the bottom switch is on, then the voltage across the load is minus V1 over 2. And then we can control the amount of time these switches are on or off, thus creating a waveform where the pulse width varies, and this is why it's called the pulse width modulation. But the switches are switched at a switching frequency which is given by 1 over Ts. Ts is the total switching period from on to off for each switch. So, the switching frequency is fixed. What we vary is the pulse width or the on and off durations of these switches, and you can see that if we do the Fourier analysis of this waveform of the voltage V2 across the load, you can get a fundamental frequency which is the AC sine wave which we want as an output across the load, and then obviously there will be higher order harmonics which are filtered out. And there are many pulse width modulation algorithms that try to reduce the higher order harmonics. But basically, the fundamental frequency sine wave is the one we are interested in. So, this is an example of a half bridge inverter which converts incoming DC voltage into an AC, which can be applied to a machine like a rotating electric motor. This is a full bridge version of the same inverter where we have now 4 switches and 4 diodes, and you can see the waveform on the right. The voltage across the load can now be V1 when the TA plus and TB minus switches are on, and it can be minus V1 when the other pair of switches are on. So, the advantage here is that the output voltage is twice of the previous DC to AC inverter that we showed you. And again, you can be interested in the fundamental sine wave, which depends on the pulse width modulation algorithm we are applying, and we have higher order magnitudes that we will filter out. So, again, by using in this case 4 switches and 4 diodes, we are able to convert DC into an output sine wave. So, by this time you have a good idea that we can implement various functions of power electronics using a diode and a switch. These diodes and switch can come in 2 or 3 different configurations. The configuration on the left side is called the half bridge module, where we have basically 2 switches with 2 anti-parallel diodes connected across a DC bus, and on the right side we have 6 switches and 6 diodes to handle full 3-phase incoming and outgoing signals. So, the basic fundamental unit for power electronics is a switch and a diode connected in this fashion. So, the question is, how do we connect them up? We connect them up in parallel using a lot of these discrete devices. Here is an example of a power module where all these devices are connected in parallel to give you higher current ratings. This is a more expanded view of the internal guts of the power module, where you can see these different chips that are connected with wire bonds in a single phase half bridge or the 3-phase configuration. Of course, attaching all these inductors and capacitors in this module leads to parasitic inductances and capacitances that we have to deal with. We also have to deal with the mechanical construction of these devices, power modules, and the stability of devices, and the fact that devices should stay on to the substrate as we cycle this module through the power cycles. So, this is the cross section of that power module. On the top we have our silicon or silicon carbide power chip, which is soldered to what is called as DBC, or double bonded copper, which is essentially an insulating layer made out of aluminum ceramic with 2 copper films on both sides, and we can pattern the top copper film to connect various silicon devices in parallel, whereas the function of the ceramic is to provide insulation and isolation between different chips. For example, between the top switch and the bottom switch. And this whole thing is soldered to a copper base plate, which is then attached through a thermal grease to the cold plate, through which we flow some kind of deionized water or some kind of coolant like glycol to cool the heat sink. So, the power, lot of heat is generated in the silicon chip here, and that heat flows down and sideways through these different layers into the heat sink, where it is removed by the water. So, the function of this power module is to connect lot of devices in parallel to give us higher current rating, but at the same time provide means of removing the heat from the silicon device or the silicon carbide device. So, now we get into the basic elements of diode and transistors. So, this one is a schematic picture of a diode, which is basically shown here as a symbol for diode, and the diode allows current to flow in one direction, in this case from left to right, and in series we show a resistance of the diode. So, the current flows through an ideal diode and through the series resistance of the diode. The current versus voltage curves are shown here. You can see that when the voltage is positive, the diode allows the current to flow from left to right, and initially takes a certain amount of voltage for the diode to turn on, and that is called V knee, and then the diode turns on, and basically we see the series resistance R on of the diode, and this is called the on state of the diode. Then if the voltage is reversed across the diode does not allow the current to flow from right to left, but a small amount of current flows through the diode. This current is much less than the current in the first quadrant, and this is called the leakage current. And as we approach the breakdown voltage of the diode, indicated here as VBR, the diode breaks down and the current goes exponentially higher, and this is called the avalanche breakdown of the diode. So, essentially the function of diode is to allow current to flow in one direction, in this case from left to right for positive voltages across the diode, and for reverse voltages the idea is to block the current, but the current can only be blocked up to the breakdown voltage of the diode. As we increase the temperature, leakage current always increases with temperature, and the breakdown voltage always increases with temperature, and that has to do with the detailed physics of the diode, which we will explain. However, the on resistance can increase or decrease depending upon the type of diode, which we will discuss later. And here are various diode structures. On the left is a pure Schottky diode, which is named after the scientist Walter Schottky. So, here is an anode material on an N-type semiconductor, which is grown on N plus substrate, and the backside is metallized and called cathode. So, the diode basically allows current to flow from anode to cathode and not blocks it from flowing from cathode to anode. Then on the right hand side is a PIN diode, where we replace the Schottky metal with a P plus semiconductor, and the rest of the structure is the same. So, in this case the current flows from top to bottom and is blocked from bottom to top, and this is called the PIN diode. And again, depending on the voltage range, we will use one type of diode over the other. All right, and then we can get into more complex structures. This structure on the left has a pure Schottky diode, but we have introduced a small amount of P region or P type of semiconductor. The function of that P type semiconductor we will explain later, but this kind of diode is called the junction barrier Schottky diode or JBS diode. And the difference between the left structure and the right structure is basically ohmic contact to the P plus. If ohmic contact to the P plus is very good, then it is called the merged PIN Schottky diode, where this P plus region is also allowed to conduct. So, this diode is basically a pure Schottky diode and a PIN diode together, and on the left hand side is a pure Schottky diode, and then PIN diode does not conduct, but is there to improve the breakdown voltage, as we will discuss later. So, moving on, here is a typical current voltage characteristics for an ideal and realistic switches. This one is a realistic switch. You can see that a switch has a current flow through the switch when a voltage is applied, and there is a control terminal called the gate control terminal. When we apply a gate voltage, then the MOSFET turns on and the current can flow across the diode as the voltage is increased, and at some value of the current saturates depending upon the applied gate voltage. So, we will study in more detail this kind of switch, but basically it is a 3-terminal device. The 2 terminals are the high current terminals between which the current flows, and the 3rd terminal is a gate control terminal which controls the amount of current that can flow. And again, this switch can only withstand so much breakdown voltage, and that is again the avalanche voltage here. And one point to make here is that there is a threshold voltage here for gate voltage. So, when the gate voltage is below a threshold, then the device is off and cannot conduct any current. In this case, I think threshold voltage is close to VG1, and when we apply gate voltage higher than the threshold voltage, then of course the current is allowed to flow. So, this is a basic characteristic of a realistic switch, and the switches come in many flavors, and we will study all of them in detail. On the left hand side is a vertical planar power MOSFET, where the current flows from source to drain, but then there is a control terminal called gate, as we discussed, which can control the current flow between source and drain. The same structure is made on the right hand side as a trench structure. The principle of operation is the same. The current flows from source to drain depending upon the gate voltage. So, these structures are very common in both silicon and silicon carbide technology. Silicon, mostly we have trench MOSFETs these days. Silicon carbide, we are mostly using planar D MOSFETs, and trench MOSFETs are in development. Then there is a structure here which is trademarked by Infineon, and that is called cool MOSFET, which is very similar to the D MOSFET we discussed in the previous slide, except the P well is extended all the way to the end buffer. The main advantage of this MOSFET is to improve the on resistance of this device, or allow more current to flow between source and drain by basically increasing the doping in the drift region. So, this MOSFET is also called the super junction MOSFET. We will describe in detail how it works and why it is better than the planar D MOSFET. And then we come to the bipolar switches. The bipolar switches are the switches which have both electrons and holes flowing into them. The previous devices I explained, the Schottky diode, the MOSFETs, are unipolar devices in the sense that only one type of carrier, such as electron, flows through this device. The bipolar devices such as PIN diode or the switches here shown are called the bipolar switches, where we have both electron and hole flow. This is a very popular switch configuration. It is called insulated gate bipolar transistor, where which is very similar to the MOSFET structure, planar or trench on the right hand side, except the substrate is changed from N plus substrate to P type substrate. And we will discuss why this helps. These devices are generally used for higher voltage applications. There are two types of other bipolar switches which are common. The first one is called the bipolar transistor, where current flows from emitter to collector, and that amount of current flow can be controlled by the base terminal and the amount of current we inject into the base terminal. This device used to be very common in power electronics, but with the advent of IGBTs, the use for these devices is diminished. Mostly designers like to use the IGBTs. The device on the right hand side is called the space charge rectifier, and another name for this device is thyristors, and also it comes as a gate turn off thyristor. We will describe all this in detail, but essentially the current flows from cathode to anode and can be controlled by the gate voltage. This kind of device again has both electrons and holes flowing into it, and it's called a bipolar switch, and is employed in applications that require thousands of amps. So, this is basically a desired switch for very high voltage, high current applications. Then finally, there is a new type of switch called the gallium nitride high electron mobility transistor, HEMT in short. It is a unipolar device where the current flows from source to drain can be controlled by a voltage on the gate terminal, but the main benefit of this kind of switch is presence of a two-dimensional electron gas, which is very high concentration of electrons that can flow from source to drain, and that is achieved by having different band gaps as we go from GaN to AlGaN. We will describe that in detail, but this switch is very common now and is being manufactured all the way up to 650 volt and is being used in many applications such as laptop chargers and phone chargers and tablet chargers and so on, and PV converters. So, this was my last slide. I hope I have given you a good introduction to what is to come in future. Basics of power electronics that require a diode and a transistor, along with passive elements of capacitors and inductors, and different types of diodes and transistors that are available to us to form power electronic circuit.